All right, so we're going to talk about the relatively simple case here of immiscible batch extraction. Remember here, anytime we're using this phrase immiscible, we're recognizing that all materials have some amount of miscibility. When we use the phrase immiscible, we're talking about two solvents that are very, very much not partially miscible, right? They're close to being immiscible, but perhaps not exactly. So we're operating in a limit where we're assuming that two solvents are immiscible, even though we recognize that to some extent there'll be some mixing between the two. Ultimately, this idea of immiscible batch extraction is analogous to the separatory funnel experiment in lab, right? We talked a little bit about extracting caffeine from tea using methylene chloride. We could shake up a mixture of methylene chloride and tea in a separatory funnel, let it settle out into an aqueous and an organic layer, and we could collect that organic layer now containing the caffeine and then further recover the caffeine from the methylene chloride solution. Industrially, this is done using mixer settler devices or processes, and the book talks a little bit more about some of the process details there. The key thing, though, in this particular case is we're just going to combine material and energy balances with equilibrium data, right? And so if we're, sort of holding this immiscible approximation, that's going to simplify things a little bit. But ultimately, our mass balance is pretty straightforward. We have some amount of feed that's charged into the separatory funnel. It's got some concentration. We'll call that X sub F. We're going to also add into the funnel some amount of solvent. Perhaps that will have some solute in it, perhaps not, but we could take that into account. And then we're going to ultimately end up with a raffinate phase that has some concentration X and an extract phase that has some concentration Y. And generally speaking, what we're going to do here is we're going to do this mass balance on the solute itself. And so, for example, the S times Y term may cancel out in this particular case. If we are in a situation, though, where the immiscible approximation holds, then we can say that ultimately the amount of feed will be equal to the amount of raffinate, and the amount of solvent we add will be equal to the amount of extract that we recover. Right? Basically, we're saying here that in this case we've got a situation where we're essentially not changing the amounts of the two different phases. All that's happening is we're moving some solute back and forth. And so that allows us then to set up an operating equation. All right, so we find this is negative R over E plus Y sub S plus R over E times X sub F. And there should be a hat on top of the E there. Make that a little bit clearer. All right, so that's our material balance, and then we're going to solve that along with equilibrium data, right? So we need some function or some expression for y as a function of x, and what we're ultimately going to do is come in and solve the material balance and the equilibrium simultaneously, and that's going to give us an expression for or a result for the concentrations of x and y left over in our funnel. We have two equations and two unknowns in this case, and that would allow us to say what happens at the end of our immiscible batch extraction. Right, this equilibrium data might just be a distribution coefficient, right? It could be a situation where y is equal to kd times x or something like that, right? It might be that simple, but this is what we're talking about in terms of immiscible batch extraction. Furthermore, we could come in and define a fractional recovery, And in terms of thinking about this fractional recovery, we're going to define this as 1 minus x over xf, right? And so essentially what we're asking is, what is the fraction of solute that's recovered in the extract phase? And so we're going to use raffinate concentrations to show that. So for example, if none of the solvent moves into the extract phase, then x remains equal to x sub f and the fractional recovery is 0. At the same time, if all of the solute were to move into the extract phase, then x would become equal to 0 and the fractional recovery would be equal to 1, or 100% of the solute would be recovered in the extract phase. So again, we're going to recognize that this immiscible assumption is something that we need to think about as to whether this type of approach is reasonable or not. But ultimately, this is how we would handle batch extraction processes similar to what we might do in an organic chemistry lab in situations where we can consider the two solvents to essentially be immiscible with one another.